So my talk is not about the cloud at all. This is a lie, but apparently the other guy's cloud talk, which is actually very similar to mine, only much smaller scale, is trendier than mine. But anyway, so my name is Greg Lindahl, and I'm the CTO at Blekko. And Blekko is a new web-scale search engine that probably most of you have not heard of. We've gotten a lot of press recently. We actually announced yesterday that we've closed a $30 million round of funding, in addition to the 20 we've already raised before. And so there's a lot more fun in my immediate future, buying yet another big cluster. What we have right now is a cluster of 700 servers with about 5,000 disks. That totals 5 petabytes of spinning Rust and about 100 terabytes of flash. And so this talk is about running a database on that sort of cluster. So the word large appears in the title, and just like the word big in big data, it means radically different things to different people. So I'll say that if you refer to your disk drives as the fleet of disks, then that's a large cluster. And so at least 1,000 devices. I'm at 5, but the big boys, like for example, Google, so the rumors say, builds clusters that have 25,000 bits of spinning Rust in them. So they come very large, and everything changes when you're at that sort of scale. I used a bit of jargon in the title, an R3 database. Alas, while all the major NoSQL databases have this concept of dividing the data into pieces and having 3 copies of each on different servers, they all use different terminology to refer to these things. So I have my own. And then finally, I won't be talking specifically about any particular NoSQL database. We actually wrote our own in-house because we're crazy that way. But what I have to say pretty much applies to all the R3 NoSQL databases out there if you're at large scale. But before I get going about NoSQL and R3, I want to hate RAID. So there's a lot of things to hate about RAID. So if I want to have attached storage on my servers and I want to put 1 disk per server, then I'm like, oh yeah, I need RAID to make it more reliable. Well, that means I have to buy 50% more disks to get RAID 1. And so that's a pain. It doesn't scale to smaller servers very nicely. When you have a failure in a RAID system, if you only have 1 parity disk and no spare, you get this annoying page in the middle of the night that somebody has to go to the data center and stick another drive in something. And that is no way to run a large data center. Your system should degrade gracefully if it has failures. And even if you have 2, so if I have 2 parity disks and 1 fails, that means, oh, if I have a second failure, I'm sort of in the danger zone. So even if you have 2 parity disks, which means that the minimum number of disks on your server becomes 3 instead of 1, you still have this ominous threat whenever there's a failure. On RAID systems, when you have a failure, it causes degraded performance for a very long time as it's reconstructing the parity. Ideally, that would be a much shorter time. Running RAID actually hurts your performance all the time, so you actually pay a tax on both reads and writes. If you go and you compare, I've got a 6-disk RAID system on a controller, and you compare that to 6 independent disks just plugged into the ordinary motherboard SATA controller, and you sort of make 6 different file systems and run an I/O test, you'll discover that you're paying a significant RAID tax on performance all the time for reads and writes. And then finally, RAID doesn't do the thing you need the most on a large system like this. It doesn't protect you against a server failure. So you have to have your data on multiple nodes, and if you're going to have software that handles data on multiple nodes, why don't you make that software do the thing that RAID gets you, which is protection against a single disk failure? So what's the alternative to having RAIDed storage systems? So that's the alternative is R3. So I divide my data into chunks, and I have 3 replicas of each chunk, And I happen to call these buckets. Everybody else calls them something different. And so you need something in software to keep these different chunks on these different servers consistent with one another. And that is what your database does. So that's sort of the source. It takes the place of RAID in your servers. And so R3 actually fixes all the complaints I had on the previous page. So it scales down to only 1 disk per server. It protects against server failure, which was the feature we were missing in RAID. The degradation in the face of failures is actually very gradual. In fact, you only have to replace disks maybe once every week, once every other week. You know, there's no urge anymore to that you have to go and actually repair things quickly, which is very nice. You can use an employee who doesn't have to have a pager, doesn't have to, doesn't ever get called in the middle of the night. They always show up every Friday and replace disks. If you have a failure in a rebuild, you can actually use the entire cluster to do the rebuild instead of just one server, and so it can be done much more quickly. And then finally, you get superior read and write performance. So the first objection that a person who's never thought about R3 before is that, oh my God, it's going to cost me 3 times as much to store my data. And that actually isn't true, because on the clusters we're talking about, generally, they have substantial RAM and substantial CPU resources because it's providing the web server and the application server and the database are sort of all on the same set of machines. And when you do that, the amount of money you actually paid for the disks is a small percentage of the total cost of your server, as long as you have enough spaces available to plug in disks. So if you wanted to buy an ultra cheap one-use server that only has 2 disk slots, changing 2 into 6 is actually annoyingly expensive. You have to go to a 2U design all of a sudden, blah, blah, blah. But if you already have fat nodes that are 2U anyway, you usually get 8 or 12 disk slots in that sort of circumstance. And so filling in all the disk slots instead of only using a fraction of them doesn't really cost you that much money. Right? You have to pay for a case, a motherboard, CPU, RAM, disk, network. And actually, on that list, the disks sort of vie with the motherboard to be the cheapest thing. If I have more disks, I get more read bandwidth, and that's a good thing. A lot of databases, you're running a MapReduce job, and MapReduce always does a lot of reading. Sometimes it does a lot of writing, but it always does a lot of reading. And so having that additional read bandwidth is a really great thing. Alas, you don't get any more write bandwidth, because every time you write data, you have to write it on 3 disks. And alas, 2 of the disks are definitely going to be remote to whoever's writing it, maybe all 3, probably all 3. But at least 2 are guaranteed to be remote from the server you actually initiated the write from. And so that actually costs you a network bandwidth. But you have to pay that tax anyway, because you have to protect yourself against the failure of an entire server. And that always means using network resources to do that. So what happens when a disk fails in an R3 system? You have the moral equivalent of a RAID rebuild at that point. So every single bucket that you have on that disk needs a new replica made. And in a RAID system, the equivalent is, so I had a parity drive and some data disks, and one of the disks fails, and so I have to go put it in a new drive, and I do a rebuild, and it actually has to read all the data on all the drives on the server in order to write parity to the new fresh drive you just put in. And so that means the time it takes to do the rebuild is the time it takes to read all that data in on a single server. So let's say instead I have an R3 system and I have 10 buckets on a disk. So if that disk fails, that means 10 other nodes remote from me on the cluster each need to take one of their buckets and make a copy on another server across the network. So there are 10 pairs of systems involved in the rebuild, and it only takes 1/10 the time of a RAID rebuild. So this is very nice. So instead of taking one server and making it basically useless for the time of the rebuild, Or if you make the rebuild really slow and use only 10% of the bandwidth, then it takes forever to do the rebuild and increases your window of vulnerability. Instead, I can do a rebuild over my entire cluster, and of my 700 nodes, only 20 of them are involved. So it's only a modest decrease in the overall sources available, but it's smoother than the RAID rebuild. RAID rebuild is very intense on one node, and by spreading it out, I keep my overall performance and response time more uniform. I think actually one unique thing about our system is that we actually have a small number of these buckets per disk. It seems that most other NoSQL databases use a much smaller chunk size. So rumor has it that Google uses a 1 megabyte chunk size, for example, when it has things that it replicates. So a little piece of jargon in order to help reason about what's going on here. So we call the R level of the entire cluster the minimum replica count of any bucket. So if I have 8,000 buckets and 8191 of them have 3 replicas, but one bucket only has 1 replica, then the R level of the entire cluster is 1. And that means you're at risk. And I'll explain in a minute about sort of the failure modes. But if every single bucket has 3 replicas, then I know that if I have 2 failures of individual servers, then I'll definitely be R1 when I'm done, and I'll still be able to get at all of my data. So as long as I have R1, I can read my data still. R1 is very scary because that says, oh my God, I've got 5,000, 10,000 pieces of spinning Rust, and if any one of them fails, I might not be able to get at all my data, and my site is down in some sense. So an R1 event is the moral equivalent of a RAID failure where it's asking you, please come plug in a new fresh disk for me immediately. And so you want to avoid R1 as much as possible. Also, somewhere in between R3 and R1, you stop being able to write efficiently. Because whatever scheme you're using for consistency, if 2 of your things are gone and 1 is there, generally that means you have a lot of logging and catch up and this and that, and it sort of ends up clogging the write pathway if you've got too many R1 buckets floating around. So let's think about statistics for a minute, right? How do I actually want to arrange my buckets on my disks? So if I spread my buckets completely randomly through the cluster and I'm R3, then if I have 3 failures, it might cause R0, right? So that's if failures were random. But the failures actually aren't random because there's plenty of failures you can have that actually take out more than a server, right? So I have disks that fail. I have servers that fail. I have a single circuit of power and the PDU that it's plugged into that might fail, which takes out, say, half a rack typically. And then also I've got networking infrastructure, and generally in networking infrastructure, the cheap way to do it, which is I think what most people do at scale, is I've got edge switches in my network which are not redundant. They're top of rack switches. They serve 1, 2, 3 racks. So if that guy goes out, then you're actually going to lose all connectivity to those racks, whereas I also have some switches in the middle, and those switches in the middle tend to be redundant. So I'm not worried about the failure of the switch in the middle for R level, but I really care about the failure of edge switches. It's very rare, but you want to be able to survive that and keep your site up. So if I have several replicas of a bucket, if they lived on the same disk, or I had 2 replicas of a bucket on the same server, I'm just asking for trouble, right? And this goes also at the PDU and the network switch level. So let's position our buckets in a clever way such that we can survive a disk failure, a server failure, a PDU failure, or a leaf network switch failure. And while we're at it, let's actually add some convenience for our sysadmins, right? So we have this fault-tolerant system, and people have to do work on systems, right? And so, oh gee, there's a new release of the Linux kernel that has an important security fix, and I have to reboot all my nodes. Well, wouldn't it be nice if I could do that reboot while my system was live and running, right? That's the best way to do it. And so in order to do that, it's nice to have something where the sysadmins can understand, if I do this, then I know the site will stay up. And so let's make some rules for how we locate our bucket. And these rules can be enforced by a daemon on the system because they're actually pretty straightforward, right? So I'm only going to put, for a given bucket, I'm only going to put one replica on a disk. I'm only going to put one replica on a server. I'm only going to put one replica on the set of servers that are plugged into a single PDU with a single circuit. And I'm only going to have one replica per leaf switch. So in our setup at Blekko, we have 16 nodes per rack and 48 port switches that serve 3 racks. And we only put one replica of a given bucket into that failure domain. So that actually leaves me with a bunch of failure domains, and actually for convenience for the system administrator, you actually want a very modest number of failure domains, right? If you've got guys that you hired to come in to upgrade the memory on your nodes, it's very nice to be able to say, those 9 racks over there, you can, all those servers are powered off and you can go work on them now, instead of pointing at only 3 racks. You get a much better economy of scale. So we actually divide our cluster up into 4 groups of racks, and we call them zones. And again, of course, every NoSQL solution has a different terminology they use for that. So we have 4 of these in a cluster, and that means I can take down a bunch of racks at the same time. So now you can have a reasonably simple rule for your system administrators to understand when they can and can't do things like rebooting systems in your fault-tolerant cluster. So if the cluster is at R3, the sysadmin knows they can pretty much do anything they want, as long as it's not to too many servers, right? So if I do anything inside of a single zone, if I reboot several nodes that are in the same zone, then I'll fall to R2 temporarily, and I'll come back to R3. So I haven't gone to R1. There's no alerts go off. You know, Greg doesn't get paged. Greg doesn't get a phone call. But alas, there's usually something that's gone wrong in your cluster. The clusters actually spend a lot of time at R2 because a modest number of buckets have only 2 replicas because there was a disk failure recently. And the larger your cluster, the more common this occurrence is. So if you're at R2 and the admin actually knows, there's only one bucket that's at R2, if the system administrator knows which zone it's in, then they actually have an idea of, well, gee, if I cause additional failures in that same zone that's already weak, then I won't cause a loss in R level. So yeah, it's safe to reboot that server even though we're at R2. It won't cause R1 and it won't cause all the pager events to happen. And that's a rule that's actually fairly simple to follow. And if this system is too complicated for the system administrators to actually work on it, then they will cause failures by making mistakes. And so at the end of the day, what you really want is a what-if tool that says, look, I'm going to go do the following maintenance. I want to reboot all the systems in this rack. What's going to happen as a result of that? And it's pretty straightforward to write a little tool that comes back and says, well, you're going to be at R2. There's going to be 16 buckets, which will be have only 2 replicas if you do that. And that tool is enough to allow a system administrator to be able to actually get their work done without causing a failure. So sometimes usually failures happen with no advance warning. And so it's very important for your system to deal with that gracefully. But if you know in advance you're going to have a failure, or if you're going to cause a failure, then it's really nice to be able to have that not cause a reduction in R level, right? Why would I want to go to R2 if I could avoid it? And so there's this concept of abandoning a host or abandoning a disk. So typical occasions, so in addition to the system administrator wanting to reboot in order to get a new kernel, there are other circumstances here where you might know in advance that you have to do something to a node. So if you have a disk that's spewing errors into your system log and you can't get rid of it, if you have smart complaints from a disk, it comes up and says, oh, back up your data now because the smart short test failed. So that both of those affect disks. Then affecting your node, if you have a DIMM that's going bad, that causes a large number of ECC events. Not only can it make your node run annoyingly slow, which is bad, but you know that eventually, right, it's going to end up in a failure. Sometimes you have systems that actually have failed DIMMs in them. This is actually really common after you've done maintenance on a node. You know, nodes, they weigh 50 pounds and yet somehow they're fragile. How's that work, right? So you've taken the node out of the rack and you put it on the floor, you did something to it, you put it back in the rack, and in the process, it's not so unusual for it to come back with you know, missing a DIMM. And when I say not that unusual, so I've got 700 servers, and if I take all of them out of the rack, it's pretty much going to be at least one that has this when you plug it back in. And in our system, missing a DIMM is a fatal error because we use so much memory the way we run things. We're like ridiculously close to the line. We have a very large amount of locked memory on every box, and missing a single DIMM means our app doesn't fit in the box anymore, and it starts thrashing. So if we see a failed DIMM, we have to, you know, stop using that node, and preferably without, you know, causing our level to drop. Also, sometimes you can actually see, oh, I've got an over temperature event, which is very serious, or I have a fan that appears to have 0 RPM, but it's not supposed to, and, you know, damn it, did we not plug in the little thing that's the sensor, or is it really dead? So what you want for that is a tool that tells the repair daemon, hey, you know, the buckets on this disk or on this system, go make a 4th copy of all the buckets in the system, and when that 4th copy is done, I want you to drop the replicas here preferentially. So that means eventually, and eventually it's not that long, right? It's the time it takes to copy all the chunks, which since the entire cluster is involved in doing the copy, this doesn't take very long. So eventually the bad disk or the bad server is idle. And then you're still at R3, and you know if you go work on that node, you're going to remain at R3. One of the trends these days is to have tools that actually automatically do things like this. So you can come in our system, you can, as an administrator, you can tell it, you know that you want to do work on a certain set of nodes, and so you could abandon them by hand. But actually, we also wired it into our monitoring scripts. So if we see a disk error on a disk, then we immediately abandon it. And that generally means that it doesn't really cause us any heartburn. It's almost as good as failing it immediately, but it doesn't cost you any R level. And then finally, if you detect that there's actually corruption in a given chunk, you can use the same technique to repair that chunk by not using it and then throwing it away without causing danger that you'll fall below 3 copies. One thing to be said about operations is that if you have a more idiot-proof way of making it, that's better, because even people who are really smart and are pretty consistent have bad days. And if you have a bad day, you don't want to be the guy there standing there. Have you ever run into this? There's a guy like in your data center, and he's like holding down the power button, and you're like, why are you holding down the power button standing there? And the guy's like, well, I meant to reboot this server, and I pushed this guy's power button in, and so as long as I stand here and hold the button, the server's not going to go down. Well, actually, that joke worked 10 years ago. These days, if you hold down the server button, it'll eventually go off. But I've never been that guy, but I could imagine being that guy. And so it pays to always abandon the server before working on it. And you can make it completely idiot-proof by telling your maintenance guy, whenever you work on a node, it's going to be the one that's powered off already. And in order to get there, what you did was you abandoned it, and then you waited until it was completely idle before you turn it off. So we actually don't do that all the time. In practice, I think a lot of system administrators really love juggling knives, and they're pretty good at juggling knives. They only occasionally cut themselves, and so they have a hard time bringing themselves to juggle knives, which are not sharp. But we actually do, in order to reliably remove the right disk, we do have a little script that blinks all the lights on all the working disks on a node, because it's just too easy to unplug the wrong disk. And that's a big whoopsie. So your little daemon that makes sure that you have 3 copies of everything, there's some minimum features that it needs to have. you need to be able to tell it to stop trying to make more replicas because, yeah, you know, a third of the cluster is down and you need to make a lot of copies, but that's only temporary. Those nodes are coming back, and so it doesn't, you're already under performance stress because you only have 2/3 of the resources available. You don't want to waste necessarily any additional performance trying to make these copies that will turn out to be unneeded. It's nice to be able to administratively kill all the copies that are in progress. Generally, this replicator also has a load balancing function to make sure that all the disks in the system sort of have an even amount of data in them. Or if you have heterogeneous nodes, it tries to keep, you know, more data on this guy because he's more capable than this other guy. And it's nice to be able to stop that from going on to keep a minimum number of changes going on and to be able to separately kill load balance copies. And I'll give you an example of using these in a minute. And then finally, it's really nice if the repair D can actually notice that, oh, gee, you know, this disk failed, rather this node failed, and I started making a copy of all the data that was on it. But you know, it came back 5 minutes later because it was an unexpected reboot. And so all the copies I started are not needed, and so let's discard them all before they complete. And that's very handy for minimizing the amount of unnecessary work the repair daemon does to your cluster. So how's a big upgrade work? I want to come in and I hire people, and alas, I've done this too many times. I want to add an SSD to every node. I want to throw away the shitty static card that I bought and put in one that works. I want to upgrade memory on a node. I want to upgrade the BIOS on a node. I want to upgrade the firmware on my SSD. And so we've done this really too many times. So what you do is you stop your repair daemon. That allows you to, you can power off an entire zone. Your cluster goes to R2. And it's not wasting any resources on trying to repair a situation that will be eventually going away. You do the work. You power on all the nodes, and you bring everything back up, and you hope that you'll make it back to R3. So for those of you who've ever done this, you know, nodes have an increased chance of failing when you've just power cycled them. And that's because you can have a power supply that's walking dead. You know, it works for supplying power, but it can't actually power on again. And another interesting trick is that if you've got a bearing problem on a disk, it's not necessarily capable of spinning up, but it's capable of staying spinning. There's a little bit of physics there having to do with, you know, friction on a sliding surface versus a static surface, which I have to mention because one of my colleagues from graduate school is sitting in the front here. We're astronomers. So these things, they fail when you work on them. And so, alas, that means you come back at R2 and you're like, okay, what's the damage? And you pull out your what if tool and you're like, okay, what if I power down these additional 6 racks? Is it going to actually cause me to fall to R1? God damn it, it does. Okay, here's what I have to fix before I do that. Okay, so assuming you can actually get back to R3, you can take on another zone and work on it and so forth till the end of the day. And then when you're done fiddling with everything and you've got everything back up, you can start the repair daemon again. And this is when you're doing this kind of forklift upgrade, there's no way to really idiot-proof it. You know, you can't have a really simple rule because you've stopped the repair D to make sure that these unnecessary copies are not done. If you have a real failure in the rest of your cluster, you need to make sure that gets repaired without causing the other stuff to be repaired, blah, blah, blah. And so my suspicion is that anybody who has a bunch of these clusters actually has a pretty sophisticated thing that automates as much of this as possible to repair the things that ought to be repaired and not repair the things that shouldn't be repaired, blah, blah, blah. I haven't quite gotten there yet, but probably in another year I will be. So let's say I want to restart my entire cluster. So that might mean restarting all the software. It might mean rebooting the nodes. So zones are also handy for doing this too, right? So I can restart or reboot a zone at a time. And fortunately, since I haven't actually powered the nodes off, I usually don't have the enhanced failure rate, and this one works better than the previous slide. Of course, so after ... I have to have profit, right? And we actually don't do this one zone at a time. We actually do two zones simultaneously when we do this, because it turns out that, hey, if you have an R1 cluster, it's still capable of serving results. It does temporarily interrupt writing when you go to R1 in a real way. But right now, because we don't have that many actual users, we're search engine, right? We're like Google, only much, much smaller. Big cluster, not that many customers. So we can do this at R1. But if you need the capacity in your cluster because you actually have significant user traffic and that keeps your cluster more than 1/3 busy, then you have to do it, or 1/4 busy, then you have to do this slowly in order to keep your capacity up. So I mentioned a checksum failure earlier. So one thing that RAID gives you that you think is a really great feature is it says it's better at detecting errors than a single disk, right? But most RAID systems, how do they do it? They actually depend upon the disks to report errors. And as we all know, disks are lying liars, and you give them bits, and they might give you back bits and claim it's the same thing, but it's not necessarily so. And if you have a small system with only a small number of disks, you probably have never really noticed this happening. If you have a large number of disks, this happens on a regular basis. And when this happens and you're in a RAID system, if it is not doing additional checksumming, which there is this funky checksum thing available, and only a modest number of RAID systems use it. If it's not using that, then it's depending on the disk, not lying when it comes back, and all hell can break loose if you get back the wrong bits and there's no error associated with it. In order to first, because I don't have RAID, I need more error checking, but also because I don't trust disks, because disks are lying liars, and the firmware engineers for disks are not necessarily the best programmers in the world. They're better than BIOS programmers, but that's not saying much. You want strong checksums available to you whenever you write something onto disk. So a strong checksum is one that is better than TCP, and you can afford to do it because writing something on the disk takes a lot of time anyway. So doing an additional thing that makes that take a little bit longer is not a problem. But that strong checksum for things written in a disk isn't a good end-to-end checksum, and end-to-end checksums are really what you want, right? You want to know, damn it, I did this right, and then I read it back a month later, and it's passed through many systems since then. There were, there's 3 replicas out there that hopefully are the same, and so forth and so on. So it's really nice to have a weak checksum available, and if you use one as dumb or as inexpensive as the TCP checksum, you can always afford to do that. Right? It's just a one's complement add or something. So if you work this into your object serializer, then frequently you can do it transparently without ever really having to think too hard about it, and then you get a nice end-to-end checksum. So we do that, and in practice, with only 5,000 pieces of spinning Rust, I fear the disk giving me the wrong bits, but I've never seen it. But the weak checksum, I get a couple of those a month. And so the reason I get a couple of those a month is because, those little network chips that offload the checksum computation to be faster, well, what if there's an error in the chip? A cosmic ray came by and the chip has parity, so of course it's, protected against that. But the reality is you get a significant number of errors. And the thing that was supposed to save you from that was the checksum, which has been offloaded, which makes it useless for protecting the data in between the networking chip and the CPU. Okay, so the fact that your weak checksum was done on the CPU and is checked by the CPU and not offloaded is what allows you to detect that error end to end. And I see these, frequently. And if you get that error and you get the error in the wrong place in your system, like for example, in your mapping protocol. So Amazon had a big S3 outage some years ago because their gossip protocol got some bogus information in it that lived for a long time. And it wasn't until they turned off everything and then brought it back up that the bad information disappeared from their system. So there's two lessons from that. The first is don't write a system where that information persists like that. They didn't learn that lesson. But the other one was, do these checksums, and they actually had checksums, but somehow the checksum failed to detect the problem. And I don't remember the exact details, but it's okay as a search engine if some unimportant website is garbled, a little bit when it comes up on our results, or doesn't come up at all. Nobody cares. But if it's in the metadata that controls your cluster itself, it can take your site down, and you don't want to do that. Another reason to use checksums is so we have all these MLC flash disks and in our cluster, right? And so you're depending upon not only a device which is incredibly error prone, because that's what MLC flash, its virtue is cheapness, not quality. And again, you're depending upon a firmware engineer who writes code for that little embedded thing on the SSD. And again, they're better than BIOS writers, but that is weak praise. So I don't trust those guys, and so I definitely want a strong checksum around everything that I read off of SSD. Okay, so I hated on RAID at the beginning of the talk, and I don't actually totally hate RAID. So one nice thing a RAID system does is it scrubs your disks for errors. So if you have checksums, that means you can scrub your own damn disks for errors in an R3 system, and you should. One problem that you have is basically you end up with sectors that can't be read, and if the disk thinks that that sector has data on it, then it will not be able to put a spare into place because that way it would take your data and turn it into all zeros, and it would be bad. It's not supposed to do that. And of course, the disk only has it doesn't have a very good idea of which blocks on the disk are really actually in use. So it'll sometimes be it'll have its panties in a wad over a sector which actually is not being used by any file, and that's a shame. But in any case, so your RAID system makes these things disappear, and if you have 5,000 disks that aren't rated, you'll see this all the time. And in order to fix it, what you have to do is you have to overwrite it. So if you overwrite it, it can put a spare in. And if you've been using disks for a long time, disks used to have 256 spare sectors that were sort of on the end, and the main annoying thing about them is that if you had a bad block, that means you'd have this weird seek to the end. So disks don't work like that anymore. So when these days, so they tell me, when you read a track off of a disk, it actually reads 3 tracks. Then when it's through reading the one revolution, it uses a DSP to do these really complicated computations to figure out what the data was for those 3 tracks. And in this environment, they have like 20% spare sectors. So these things are going bad all the time. It's successfully covered up by the disk, except in the case where even though it tried a bunch of times, it couldn't read that sector, and it thinks that sector is in use, and it throws this offline uncorrectable sector error. So you need to write that sector in order to allow it to be substituted. Whereas your RAID system, right, it went and it was scrubbing your disk. It got an error reading it, and so it went and it consulted with all the other disks, figured out what the correct data was, and wrote it, and that allows the disk to replace it. So you have to do this yourself. So fortunately, there's a bad block how-to that explains how to do this. So you pull the sector number out of the error message, and you compute the location within your disk, and you write zeros onto it, and you're done. Well, so if that sector was in use, that means you just damaged a file. If you, or even worse, it better not be part of the file system metadata. But if you have checksums, you're protected against having hurt a file. You're not protected against the metadata. Or the how-to explains how you can write a little tool that prints out what the file name was of the file that's damaged, or will tell you that the file system metadata is involved. It's a small chance the file system metadata is involved because almost all the blocks on the disk are used for data. Yeah, so this is something you have to do that you don't normally have to do, and not that many people do this, so it's not really discussed that much. It's kind of a niche thing for people who have a lot of disks and no RAID, which is unusual, but that's how you fix it. So disk controllers and failures. So in this world of no RAID, you use whatever disk controllers you have available, and you use them in JBOD mode, where you have a file system, one file system per disk. And in an ideal world, even though one of your disks just exploded, if it's not the system disk, you would like the node to stay up with its n-1 data disks and to carry on as best it can. Also, if there was a failure on a node that wasn't the disks, you'd like to be able to take the disks out and plug them into another server and have your spare server. If it turns out you went to R1 and there's several replicas that were on the guy that failed, or even worse, you're at R0 and the thing you're missing was on one of those disks in the failed server, it'd be nice to be able to move those to another server. You actually have to test all that stuff these days because you get fancy controllers and I don't know, HP successfully made a really low bid, and so I bought, of the 700 servers, 500 of them are HPs. And because I wanted 8 disks, they couldn't use the motherboard controller. And the motherboard SATA controller is a thing of beauty. It runs really fast. It doesn't really have any bugs in the drivers. It doesn't really have many bugs in the chips. And the expansion cards you get, if you want more than 6, all sell in much lower volume and are lower quality from what I can tell. So the HP 410i in particular has this talent for sometimes when you have a random disk fail that's not the system disk, it takes out the node. And that makes me very sad. It also, even though if you configure it as a JBOD, and then you pull out a disk and you put it into a different server, it insists on erasing it. Because, well, if you had a RAID set, that's not a valid thing to do. And I've been yelling at people who write this software for these things for 16 years, and I've never been able to convince anybody to allow me to move my fucking disks around. My disks, let me move them. Another piece of advice is do not use any controller that has the word Marvell on it, because, well, I can tell you the sad story, but that's, remember I mentioned when I had to power down the entire cluster to replace the SATA expansion card, that would be the Marvell ones that I pulled out and threw away. So do yourself a favor, don't be like me, buy LSI in the beginning if you have to. If you can't use the motherboard controller all the time because you have 8 disks and not just 6, buy LSI, update the firmware, and you'll be much happier than the poor other guy who bought Marvell. Don't do that. Booting a node. So the standard init scripts, if it comes up and there's a missing, a file system failed FSCK, it hopefully gives you a little root shell prompt. That's not so good in a thing like this where you expect disk failures to happen all the time. So it's okay to let the usual init scripts mount your system disk, but for your data disks, you want your own little FSCK script that, hey, if the disk is bad, that's not a problem. Come up with what you have and soldier on. Because in this environment, you're not necessarily replacing your dead disks for a week or two. And so it's not so unusual to reboot a node with a dead disk in it. And you're totally okay with that being missing. And while you're at it, when you're booting, run a performance test on every disk while they're idle before you've started the database. And that gets you sort of 2 things. First, there's this concept of a sad disk, which is one that just runs slower than it ought to. And in an ideal world, Smart would have told you that it's having a bunch of errors when it tries to seek, but it seems that never works, and at least on the fleet of disks I have, that never fucking works. And so you can have this disk that's running at 1/10 the bandwidth of all your other disks in the cluster with no sign other than that it's behind on the work that it needs to do. And so having a test allows you to figure this out, at least at reboot time. You really want a continuous monitoring infrastructure that would figure this out while the node was up, but at the very least, you can figure this out when you boot. Secondly, this serves as a good regression test. So we run CentOS 5, and CentOS, like Red Hat Enterprise, has these little point releases for the kernel where they add in new drivers and they fix security bugs, blah, blah, blah. And somehow, several of the point releases in CentOS 5 caused a significant decrease in disk performance. And then in the next point release, it would come back and be fine. And there's nothing in the release notes that indicated how they managed to screw the pooch. And in order to regression test for this, the easiest thing is to do it when you boot. And that way you can't be missing, and it's like a 20 to 30% degradation of performance, and Definitely don't want those guys floating around your cluster at random. Monitoring the database. So you want to monitor database-specific things. So the R level, hosts appearing and disappearing from the cluster, disappearing from the cluster, appearing in the cluster, things not draining as fast as they should. The success of the write path for actually getting stuff written because you're well above R1. Progress of your MapReduce jobs, blah, blah, blah. Trash, the merge process. So trash. So conventional SQL databases generally don't ever have to delete a large file as part of what they do. And that's for a reason. That's because the OS usually freezes I/O, at least on that file system of that device, but maybe for the entire system, when you do an RM of a really big file. Because it's doing all these metadata operations that need to be done before it can do the next thing on its list. And so it has to be done immediately, basically. And so how these NoSQL databases that work at large scale are usually implemented using a hierarchy of files that are individually sorted on the primary key. So I have the data I wrote last week is in this huge file, and then the data I've written recently is in this little file that eventually is going to get combined into the big one. And so as you merge these files together, you end up deleting really big files. And if you're only doing batch operations, this is not a problem. But if you're doing both interactive and batch in the same database, which we do all the time, you have to slowly delete that file instead of quickly deleting it. And what we do is rename it into a trash directory and have a daemon that does nothing but open files and slowly trunk them smaller and smaller until they disappear. And that's taking out the trash. I'm going to skip over the debugging thing, even though it's very important, because I'm almost out of time. So we've run the system as I've described to you for 3.5 years, and we've never actually had gone below R1 due to a hardware failure. And that's even though we've actually taken all the boxes down about 5 times to do something in them and incur the additional failures you get during that. So if you're mucking with your database software, of course you can cause R0, and we've done that repeatedly. But we've never actually lost any significant amount of data in our database, despite the fact that we were developing the database in addition to running a search engine, which we were developing on top of that database at the same time. So we've never actually had significant downtime from this. Almost all of our downtime is caused by our network switches deciding to hang and the configuration problems with setting up a redundant network interface, right? All this, to talk to the outside world, right? All this great failover stuff usually causes downtime when you're setting it up. Gotta love it, because it's fault tolerant, but it causes faults. And I have a few funny problems, which I do have time to say. So we found a bit pattern that would not pass through our 10 gig switch. We noticed this because we had a particular bucket that would never copy. And that's because at the very end of the bucket, like the last thing it did was a fragmented UDP packet, and the 5th fragment of 5 had a funny bit pattern, and it would not go through. It was UDP packet. So how the hell you break that? It must have been a bug in the switch silicon and not the control plane. Yeah. We couldn't get an NCQ to work on a quarter of our servers because there was a BIOS bug. And of course, the motherboard vendor volunteered to roll us a special BIOS, which they would then not test for us to run in our production servers. And I'm like, I'll move my SSD to the LSI card instead. Intel SSDs, you have to boot into FreeDOS in order to update their firmware, which you have to do because there's a significant bug. There's no FreeDOS driver for the LSI card. Hoist by my own petard. And finally, just try getting support for an intermittent error, which can't be replicated in a couple of nodes. So if you go and you start typing an email to somebody, well, on my 175 systems, I have this occurring once per week. You might as well just not send that email because you're never going to get support for it. Because they can't replicate the problem. And that's pretty much all I have to say. So, any questions? In the back? Yeah, I actually meant to say something about that. So it's funny. So everybody who does this has to decide what the number of the counting shall be. and they actually all choose 3. So here's why. So if I have 2, I don't have enough redundancy available in my system, and it's too easy for failures to cause me to lose a piece of my database, and that just sucks. So you can't count 2 unless you go on to 3. 4 is oh God, I'm forgetting. I know what 5 is right out. What's 4? You don't count 2 lest you go on to 3. Anyway, 4 is too expensive. So yeah, 4 is more resilient to these problems. And if I had, maybe if I had 50,000 pieces of spinning rust, I would need 4 in order to operationally succeed and never going down to 1. But I've never seen anybody have a large enough scale that they sort of got forced to do that. So 3 is the sweet spot for everybody. Excuse me? Yeah, and it's a really dumb thing, and don't do it. So basically, we have the batch side and the interactive side, and so we're like, hey, let's be smart and let's lock all of our interactive things that need great response time into memory. And so we're still on CentOS 5, so we have a really old kernel, and it's bad there because it only has one free list, and it can cause excessive the page daemon to spend way too much time walking tables. So you shouldn't do it for that reason. Secondly, if you set this up and we're only going to lock half the memory, that ends up getting mission creep. And so now we've locked 95% of our memory once I gave the programmers the ability to lock more. So this creeping thing will always kill you. And when you only have a few % of your memory available for paging, your nodes are awfully close to thrashing all the time. But if your locked memory just creeps up just a little bit too far, suddenly you have nodes locking up or falling over because of it. So I do not recommend doing this. It's a... Excuse me? Yeah. Yeah, so if you have a page of your program text that's paged out right, it can take a considerable time. If you go through a code path you haven't been in a long time, you have to wait for a disk operation. And the system disk, we use the system disk for database loggings to make things durable. And so as a result, it's kind of busy all the time, and so you really don't want to swap that program page. And I went tonight to the Linux kernel summit and our collaboration summit, and I whined about this, and nobody had any sympathy because they're like, look, use a modern kernel because it does all this a lot better. So I have high hopes that when I actually get CentOS 6 installed, that this situation will be better. Also, Artur's talk yesterday reminded me that there's a lot of interesting tuning that can be done, which I'll have to go review once CentOS 6 arrives for me.
All right, I'm afraid that's about all the time we have.